I want to take you through some of the rotational motion problems. This first one, we're going to actually go backwards and look at the classic mass on the table, hanging mass, and now there's the pulley. But now that the pulley has a mass, the main thing that it does is that it requires us to look at the tension, and we need to call that T1 and that T2. In the past, those two tensions could be viewed as internal forces. They were the same. There doesn't need to be a torque on the pulley if the pulley doesn't have a mass. But now that it has a mass, there is a requirement that there must be a torque in order to turn it. If there's going to be a torque, then this tension is going to have to be greater than this tension. And again, we'll look at the blown up version of the pulley here in a second. But let's look at the forces first. And so for the forces, we're going to look at the hanging mass. And if you look at the hanging mass and you draw a free body diagram, you're going to have its weight down and T2 is up. And since it's accelerating down, we know that the force down is greater than the force up. And so we can write an equation like that. If we draw the free body diagram for M1, we have a normal force up. We have M1G down. We have T1 to the right. And let's go ahead and put the force of friction to the left. Now the normal force is equal to M1G in this case, and that's something we usually aren't interested in, but because there's no acceleration in that direction. But we do know that T1 minus the force of friction equals M1A. And again, there's, this is T2. So we have three kind of typical variables, T1, T2, and the acceleration. So we don't really have enough if we just look at forces. So let's go ahead and look at torque. And when I mean torque, I mean the torque on the pulley. So here's the blown up version of the pulley. And what we have here is we have a rope that's pulling this way, T2. That would tend to cause a clockwise rotation, and then we have a rope attached to the top pulling this way that would cause a counterclockwise rotation. They each have their own lever arm. They happen to be the same distance. There's the lever arm for T2 and there's the lever arm for T1. They are both perpendicular, and so remember, torque equals R cross F. And in this particular case, the torque that's winning is T2 times R minus T1 times R. That net torque, and again, what we know torque causes is I alpha. Again, torque itself causes a pulley with moment of inertia I to experience an alpha, meaning to angular accelerate. And we know that the pulley has to have an angular acceleration if the objects themselves are going to accelerate. And they will, because they do have a net force on each of them. We're going to replace I by what a pulley is, 1/2 capital M R squared, and then we are going to replace alpha by A over R. The nice thing about this equation is that this is an R squared over an R, which is just an R, and then R, and R all cancel. And so algebraically, we can simplify this equation to T2 minus T1 equals 1/2 capital MA. And then to solve an equation similar to this, we would take this equation for T1 and put it here, and this equation for T2 and put it here, and then we'd have one equation with just the acceleration. So if we did that, I can't really show all of the algebra here, but T2, if you move to the other side, would equal M2G minus M2A minus T1 is the force of friction plus M1A, and all that's supposed to equal 1/2 capital MA. So this is M2G, and you know what, this force of friction, let's replace this. This force of friction we know is mu M1G, and we get that from looking at over here. We know the force of friction is mu times N, but N has to be M1G. So we get minus M2A minus mu M1G minus M1A equals 1/2 MA. These terms with A are going to move to the other side, and so we get M2G minus mu M1G equals, and I'm going to go ahead and factor out that A. This, and this are all on the other side. 1/2 capital M plus M2 plus M1. They all got multiplied by A. And then the acceleration then, if I solve for all of this, is M2G minus mu mg all over 1/2 M M2 plus M1. And that would be the acceleration of this particular system if you knew the masses and you knew the coefficient of friction. Once you found the acceleration, you could plug back into either one of the force equations to find both T1 and T2. Okay? And again, you're probably going to use forces and torques if you want to find tensions and accelerations. We could do this exact same problem using energy. The energy way to do this problem is to focus on the fact that there is energy conservation. And what we're going to do is that what is giving this system energy? Well, M2 is going to drop a certain height. And its loss of potential energy, M2GH, is going to provide this system energy. Now we do lose some energy due to friction, which would be the work done by friction, which would be mu m1g times the distance it slides. But the distance it slides over is the same amount that m2 would go down. So we'll call that h. And then what does it provide? Well, it makes both m1 and m2 get to a certain velocity after it's dropped a certain height. So you get the kinetic energy of both of those. M1 doesn't go up or down in any height, so it doesn't change its potential. And then the pulley gets some rotational kinetic energy. And again, what we would do next, and again, this equation looks pretty long, that I is going to be 1/2 mr squared, and then we are going to replace omega by v over r, and then square it. And again, you can take this equation and eventually solve it for some velocity. If you really wanted to connect those two, you could show that they're the same equations by using the v squared equation, because this is a constant acceleration, and so you can use this, and x would be h, and you could show that these two values are actually the same thing. And again, whether you're looking for forces and torques or whether you use energy, energy is usually going to find the velocity, and if that's all you need, then you should probably use an energy approach. But if you wanted to look at tensions and accelerations, you should use forces and torques. Okay, the next one we want to look at is just rolling a disc down a ramp of height h at an angle theta. Again, the disc has a moment of inertia of 1/2 mr squared. Let's look at the energy perspective first this time. Energy is actually really easy. It starts out having mgh, and then it gains both 1/2 mv squared, which they would call translational kinetic energy, and it gains rotational kinetic energy. It is pure rolling, and what pure rolling implies is that v equals omega r, and there's no slipping. Everything is a static friction, not a kinetic. There's no grinding there where you would lose energy due to heat. This is pure rolling, such that this is true, and there's no slipping involved. And so we just get this. Most of the times, you might want to solve for v, and so you'd replace I for what you know it is, 1/2 of 1/2 mr squared, and you'd make omega v over r squared. These r squares are going to cancel, and so you're going to get mgh equals 1/2 mv squared, and this is just 1/2 of 1/2, so that's 1/4 mv squared. So then that's mgh equals 3/4 mv squared. Let's go ahead and cancel the masses now, and then we can divide by 3/4 and then take a square root. And so the velocity is the square root of 4/3 of gh. And so that'd be the velocity of a rolling disc. Now, if you rolled a ball, if you rolled a hoop, they'd all be different because the moment of inertia would change and this factor would change. It'd still be very similar. Instead of 4/3, it might be 7/10 or 10/7 or something, but it would still be the square root of something in terms of gh. Now, if we did torques and forces, the thing is you actually have to choose a pivot. So as it's rolling down this ramp, let's imagine that the pivot is right here. So that means that the disc is rotating about this as our pivot point. Well, if that's our pivot point, then there's your lever arm, and we're looking at not mg, which would be down. We need the perpendicular piece, right? And so then the torque, if we do torque equals I alpha, the torque on this guy is mg sine theta times r. mg sine theta is gravity's component down the ramp, and that down the ramp is the perpendicular force based on that lever arm. The I, what's the moment of inertia of a disc pivoted on the edge? Well, pivoted on the edge, we have to use the parallel axis theorem. The parallel axis theorem says that the new moment is the original moment plus, some md squared. The d is how far you move the pivot. In this case, m r squared, because we move the pivot from the center to the edge, times alpha, where alpha is going to be replaced by a over r, just like omega is replaced by v over r. Again, it's one of those things. These are both going to have an r squared, so we're going to have mg sine theta r, and this is going to be 1/2 plus 1 is just 3/2 mr squared times a over r. That r and that squared canceled, but then this r and the leftover r canceled. The m's cancel. Then all we have to do is multiply by 2/3. So we get 2/3 g sine theta equals the acceleration. And you could check that these also agree using the v squared equation. Okay, so that's one version of the torque. Let's do the other version. So now we're still rolling a disc down. It's the exact same problem, except we're going to view the center of mass of the pivot as it's rotating. So we're viewing it's rotating about itself. In this case, our lever arm is still r, but the force of friction up is the force that's causing the torque that's causing it to rotate. And again, there's just different perspectives. If this is your pivot, then you're viewing gravity as the force causing the rotation. And in this case, if the center mass is the pivot, then you're viewing the force of friction. So we say torque equals I alpha. The torque is just the force of friction equals I, and it's pivoted in its center, so it's just 1/2 mr squared equals A over R. So we get that the force of friction equals 1/2 mr times A. Now, we can't do anything with this because the acceleration we don't want in the terms of the force of friction. But now let's look at a force equation. And on a force equation, then we are looking at the forces. And so if we look at the forces on this guy, in the y direction, if we do F equals ma, we are then looking at mg sine theta down the ramp, force of friction up the ramp, equals ma. And what we can do is we can take this force of friction and put it in here. And so we get, torque, my bad. I did miss an R in here. See how this is a force of friction, and I said it was equal to the torque? The torque is the force of friction times R, which does in fact make that R go away, and then everything looks a much better. So the force of friction, sorry about that, is 1/2 ma. Everyone see what I did? And that happens sometimes. Instead of a torque, I actually just put a force right here. The torque is the force of friction times its lever arm R, and then we have R squared over R. That R cancels with that R, and you're left with just this equation. So now let's go ahead and take this value and put it in over here. And so we get mg sine theta minus 1/2 ma equals ma, and then you're going to get the same thing. You're going to get mg sine theta. When you add that over the other side, you get 3/2 ma, and then of course you get 2/3, masses cancel, g sine theta equals a. And it gives us the same thing. So regardless of your choice of pivot, the acceleration is the same, and again, you can verify that those are actually the same value if you want to look at the v squared equation. And the distance here would be h over sine theta. And again, you can verify that this is equivalent to that. All right, let's look at a yo-yo problem. This probably won't take as long. Let's look at the forces first. First of all, we have mg down, and then we have some tension up. So from a force perspective, if we look at F equals ma, mg minus t equals ma. There is some acceleration down, and it's not going to accelerate down at g. It's going to be some fraction of g because it's got to roll and unwind down. If it was in free fall, it'd be straight up g. And then let's look at torques. Torque equals I alpha. I would view the torque, again, just let's put the pivot at the center of mass. If we put the pivot right there, then mg doesn't cause a torque because it doesn't have a lever arm. And then the tension and r. So tension times r is our torque. Moment of inertia about its center is 1/2 mr squared. Alpha is a over r. And we get the tension equals 1/2 ma. Let's put that in over here. mg minus 1/2 ma equals ma. So mg equals 3/2 ma, independent of mass, and we can show that we get 2/3 g equals a. And again, maybe you would have guessed 2/3, maybe 4/5, maybe a half, but certainly the yo-yo, when it unwinds, isn't going to accelerate at g. It's going to be something smaller than g, and 2/3 makes sense. We can look at this from an energy perspective. And the energy way says, well, it's just going to lose some energy and then gain some other energy. The energy that it's going to lose is potential, and the energy it's going to gain is both translational kinetic energy and rotational kinetic energy. Again, you're going to go through this thing where you're going to take 1/2 mv squared and rewrite 1/2 mr squared and v over r squared. And it's going to be very similar to other things we've done. Again, rolling this down, rolling a disc down a ramp, rolling it down a yo-yo, are all very, very similar, and it doesn't really matter. It's gravity versus that particular shape. And so we're going to get this exact same thing. We're going to get mgh, this is 1/2, and this ends up being the r squares cancel, and you get 1/2 of 1/2, which is 1/4. 1/4 plus 1/2 is 3/4. Feel free to go through that slower if you need to. Cancel out, and again, you're going to get v equals the square root of 4/3 of gh. And again, you can make sure that those are the same thing, verify using the v squared equation. And again, the yo-yo problem, there's lots of similar problems to it, but you should be able to analyze it using torques and forces, and then also energy. And the last problem I want to look at is kind of just looking at an unstable board here. So just imagine that this board has mass m. There's a m2 on this side, there's an m1 on this side. Let's assume that m1 is bigger than m2, and it's pivoted at not the center, but at L/4. So you can imagine this whole thing. So you got a board, it's pivoted here, and it's got more mass here than it is here, and it looks like this more mass is even further away, which would cause a bigger torque. And so this whole system is going to rotate like this. Okay, and so let's look at torque equals I alpha. Both of these things are fairly complicated to look at. So the first thing is, let's look at the forces. So we have m1g down there, we have m2g down here, and then we do, coming from the center of the board, have capital Mg down there. Now let's look at all their torques. This weight and this weight are both going to cause a clockwise torque, and this one would attempt to have a counterclockwise torque. So these are going to win, and let's call them both positive. So we have m1g, and then what's its lever arm? Well, its lever arm is how far it is from the pivot. In this case, 3/4 L plus capital Mg at L/4, and then minus m2g at L/4. I just used every one of their forces and their lever arms. And that is the torque on the system, and there is a torque, which means there is going to be an alpha. Well, how big is the alpha? Well, we have to decide what I is. Remember, I is always the summation of all the individual parts. And so let's just go through those parts. This moment of inertia, what's a point particle? So it's m2 and then its distance squared, which is L/4 squared. That's that one. And then let's do m1, 3/4 L squared. So we have the 2 point particles, whether those are bricks or doesn't really matter what object they are. They're a point particle, which means we're considering all of the mass at a specific location. And now we have the board. And the board is tricky because we move the pivot from the center. So we have to use the parallel axis theorem. Reviewing the parallel axis theorem says that the new moment of inertia is the center mass moment plus md squared, where d is the distance you've moved the pivot. If you pivot a board from the center, it's 1/12 ml squared. And then we have to add md squared, and we move the pivot L/4. So we have to add this, 4th squared. And that equals alpha. And again, all of this stuff is going to just be some random fraction. This is 3/4 plus 1/4 plus, 3/4 plus 1/4 minus 1/4, but those masses aren't all the same. So none of these things really work well together, because they're not gonna, you can't just cancel. Like this looks like, oh, it's an mg/4 and this is an mg/4, but these masses are different, so we can't cancel. So this alpha would be something, but we could solve it if I gave you the numbers. And that would be the original alpha. The alpha is actually going to be a function of both time and theta, because as you rotate down, the torques change. The moment of inertia doesn't. It's always the summation of all the pieces. But as this goes down, all their lever arms change. They actually all get smaller. But this would be some number. You could find the net torque, you could find the total I, and then you could find the original alpha. Okay, let's draw a picture of what this would look like at the very bottom. So at the very bottom of the swing, the pivot was here, then this guy would be up, and it would look more like this, where you'd still have that M2 up here, and you'd have M1 down here. And hopefully you can imagine that this thing would be like a pendulum and go whoom, 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 whoom. It'd keep just swinging on this pivot point. And what we want to find is omega max, which would be the fastest it was rotating. And again, you have to think this through, but the omega max does occur when the rod is totally vertical and at the bottom, because once you start to swing up, then the torque's in the other direction, and that would cause an alpha in order to slow this thing down from rotating, because it'd be going zero, fastest, slower, 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 stop, and then accelerate back the other direction, and so on. So we want to find it here, and we want to use energy. And so we just have to be careful when we do this. The energy, again, has to be all related to some reference point. So let's go ahead and put the reference point there at 0. So in terms of potential, we have, remember, we have M2 there, and we have M1 there at the beginning, and we have capital M of the board there. And the board is some L, right? So at the beginning, how far are they all up? Well, if this is 1/4, this is 3/4. So they're all 3/4 up. So then we'd have potential energy of M2G times its H plus capital M G times its H plus M1G times its H. And that's all we have at the beginning. There's no springs and nothing is moving, so everyone has potential energy. And then at the end, we some of the things still have potential energy. The board actually swung down to here. It's still L over 2 up. So the board, MG, is still at an L over 2. M2G actually went up. It's at a full L above. This lost all of its potential. And then what happened? Well, the system gained rotational kinetic energy. And you already know the I. This whole massive term up here, that whole thing equaled the I of the system. And that's the number you would put in here. And then if you look at it, everything is a known quantity except for omega. So you could use this to find omega. And again, we do know that it's the maximum omega. If you wanted to know the maximum speed of any of the objects, well, then you could use V equals omega R, where R represents how far they are from the pivot. Remember, the entire system is rotating at the same omega. But M1 is certainly going to be moving faster than the board center mass, which is moving at the same speed as this, because they're both the same distance from the pivot. But this one's going to be moving the fastest, although they're all going to be rotating at the same. Again, rotational speed, linear speed. They're going to be moving distance. This thing, just think about it, it has to go that distance in the same amount of time that the board has to go this distance, which is the same distance as that rotating. And again, this is a nice rotational motion question. It looks at torques and moments and how they influence an original alpha, and then it uses energy to find a maximum omega.